Hey everyone, and welcome. Today we're going to break down one of the slickest and most efficient tools you can have in your programming toolkit. So get ready to seriously level up your problem-solving skills because we are about to master the two-pointer technique.
All right, let's just jump right in. Imagine this. You're in a coding interview, you're a little nervous, and they hit you with this classic problem. You've got a sorted array of numbers and a target value. Your job is to find out if any pair of numbers in that array adds up to the target. So, what's your gut reaction? How do you even start?
You know, if your first thought was something involving nested loops, you are definitely not alone. It's the most intuitive way to think about it, right? You just pick a number, and then you loop through every other number to see if they make a pair. This is the classic brute force solution. It's simple, it makes sense, and honestly, it's kind of a trap.
And hey, don't get me wrong, this code absolutely works. It'll get you the right answer, for sure. But the problem is, as soon as that array starts getting big, the time it takes to run just explodes. We call this O of n squared, or quadratic time complexity. But don't you worry, because there is a secret, a really clever way to make this thing blazingly fast.
And that secret, my friends, is the two-pointer technique. This is the elegant, optimized approach that interviewers just love to see. It's what lets us solve this whole class of problems in a single, beautiful, lightning-fast pass.
So what is this thing exactly? Well, at its core, it's all about using two different indexes, we call them pointers, to move through a data structure like an array. Instead of that clumsy method of checking every single combination, these two pointers work together, intelligently zeroing in on the answer and eliminating possibilities as they go. And this slide really lays it all out. The difference is just stark. That naive approach, the one with the nested loops, is O of n squared. It gets slow, fast. But the two-pointer approach, that's O of n. Linear time. It scales beautifully. And the best part? Look at the space complexity. Both use constant extra space, which makes the two-pointer method the hands-down winner.
But here's the thing. This isn't just a one-trick pony. The two-pointer technique is really more like a playbook. It's got several different patterns that you can pull out and apply to all sorts of problems, whether you're dealing with arrays, strings, or even linked lists.
The three big patterns you'll see are these. First, opposite ends, which is exactly what it sounds like. Pointers start at each end and move toward the middle. Perfect for sorted arrays. Then you've got the slow, fast pointers. Some people call this the tortoise and the hare, which is a game changer for finding things like cycles and linked lists. And finally, there's the same direction pattern, where both pointers move forward, but maybe one is waiting for the other. Super useful for partitioning data.
Okay, theory is great, but let's see this baby in action. We're going to use that opposite ends pattern to solve a super common problem, checking if a word is a palindrome. So our test subject is the word level. What we're going to do is stick one pointer, our left pointer, at the very first L, and we'll put our right pointer all the way at the other end on the last L. The game is simple. We check if the characters they're pointing to are the same, and then we move them closer.
All right, first check. Left pointer is on L, right pointer is on L. Is that a match? Yes, it is. Awesome. So since they match, we can confidently move both pointers one step inward. Left moves to E, and right moves to the other E.
And we check again. Left's on E, right's on E. That's another match. Fantastic. So we move them inward one last time. Now, they've both landed on that middle V, which means our job is pretty much done. We never found a single mismatch.
And the result? Of course, level is a palindrome. And just like that, in a couple of simple steps, we solve the problem in a single pass without needing any extra memory. That is the elegance of the opposite ends pattern. Okay, so now let's bring this full circle back to our original two-sum interview question. We use the exact same opposite ends logic. We start with pointers at the very beginning and very end of our sorted array. We add up the numbers they're pointing to. If that sum is too small, what do we need? A bigger number. So we nudge the left pointer forward. If the sum is too big, we need a smaller number. So we nudge the right pointer back. It's this beautiful, logical dance where we eliminate huge chunks of the array with every single step.
So now that you've seen it work, the big question is, when should this technique actually pop into your head? Let's build a quick field guide so you know exactly when to reach for it.
Your two-pointer alarm bells should start ringing anytime you see a sorted array, and the problem involves finding pairs that meet some condition. It's also your absolute go-to for anything with palindromes or if you need to reverse something in place. And yeah, for more advanced stuff, it's crucial for merging data or hunting for cycles in linked lists.
But listen, it's not a silver bullet. You got to watch out for a few things. The big one is that this technique almost always needs the data to be sorted. So if it's not, you got to sort it first. Also, be super careful with your loop conditions. That while left is less than right part, it's really easy to get an off by one error there. And as always, don't forget your edge cases, like empty arrays or pesky duplicate numbers.
Let's wrap this up by focusing on the real reason this is such a big deal. This isn't just a small optimization. The performance gain you get is your new superpower. It is absolutely massive.
Just take a look at this number for a second. 1 trillion. That is a 1, followed by 12 zeros. It's just an absurdly large number, right?
Well, get this. If you had an array with 1 million items in it, that first clunky O of n squared solution would have to do roughly 1 million times 1 million operations. That's a trillion calculations. It could take minutes, maybe even hours to run. But the O of n two-pointer approach? It would take just 1 million operations. It would feel instantaneous.
There's a quote that just perfectly sums all of this up. It's the difference between an algorithm that is theoretically possible and one that is practically useful. And that's really what we're talking about here. It's the difference between an idea that works on a whiteboard and a real solution that works on real-world data.
So there you have it. You've seen the logic, you've seen the patterns, and you've seen the unbelievable performance gain. The two-pointer technique isn't just a coding trick, it's a whole new way of thinking more efficiently. So the only question left is, now that you have this tool, which complex problem are you going to simplify first?